Good morning. Welcome to Krishna's classroom. Now we set forward on a new program. Recall in the context of differentiation and integration and the connection between them. We had a feeling that integration is the inverse process of differentiation. This was the sort of elementary notion that we had, and we used it very extensively to compute the or get for elementary functions the integrals of element. And then, of course, with the rigorous definition of Riemann integral, this connection was subjected to deeper investigation. And then we discovered that it is not as simple as it appeared to be in the context of smooth functions, but the scope is quite large, and there is a deeper relationship between them, and we explore this to some extent. And you recall there were several shortcomings of Riemann integration, or we felt that it's not sufficiently uh, the most general scenario that you can build. And this led to further investigation on the integration theory. The concept of measure appeared, concept of integration appeared, and then we had what is called the concept of a Lebesgue integration. Now it is time we explored the problem in the context of Lebesgue integration and what sort of new ideas that emerge out of it. Okay, so this is the new chapter that we are taking up, namely differentiation and integration. In fact, they look at fundamental theorem of calculus or fundamental theorems of calculus in the context of the more incisive integration theory, namely the Lebesgue integration. Okay. So, what do we have? We are expecting to look at these kind of things. That is, suppose you have an integral of this kind. This is F derivative. We expect a relation of this kind. Okay. And again, second question is that if fx is defined as integral a to x dt, then f is differentiable. I'm very loose. This is all loose talk. It's not a precise statement I am making. Then we expect So the question is how far these results are true in the context of the new integration. That's what we are asking. Now in this context, we introduce concept of absolutely continuous functions and these kind of theorems are explored with absolutely continuous functions. A typical result is this. So let me just designate this absolutely continuous AB. This to be called absolutely continuous on the interval AB. Okay. So a typical result that we would obtain is this. Let F be maybe is a interval compact state. Then F is differentiable almost everywhere maybe we're talking about derivative. Endpoint derivative comma its derivative is integrable over and integral a to b f derivative f b minus f. Now we also prove a characterization of these absolutely continuous functions. And we have this interesting theorem. A function f on the compact interval AB is absolutely continuous on AB if and only if there is a characterization. It is an indefinite integral These are the type of theorems that we eventually arrive at. Okay. So before we go to introduce the concept of absolute continuity, we now explore the continuity properties of monotone functions. So today I think we will be dealing with that. So we look at this continuity properties of functions. The knowledge about the continuity properties of monotone functions play a very important role in this study. Because after all, it turns out that absolutely continuous function can be written as the difference of two monotonically increasing functions. And then you can use these properties in the analysis of the absolutely continuous functions. So let us state the theorem, the main theorem that we are going to prove today. Let f be a monotonic function on the open interval then f is continuous except possibly let except possibly at a countable number of points So this is what we want to observe first. That means if you have a monotone function means two things. Either it is monotonically increasing or it is monotonically decreasing. In either case, this is what you obtain, that the function is continuous almost everywhere. This is except on a countable collection of points on the interval Now, this is a fascinating information about such functions. So, we will prove this result. So, we are now going to talk about functions of this kind. So, we will look at what is called a monotonically increasing function, then possibly it may have some jump discontinuities. It is not necessarily true that these monotone functions are continuous. Monotone functions may be continuous or may not be continuous. But if it is not continuous, it has points of discontinuity. And the points of discontinuity are countable because of that is the uh, constraint that is imposed by that the property of monotonicity. Okay. Now you recall the Dirichlet system, which is 1 at all rational points on the interval 0, 1 and 0 at all irrational points on the interval 0. Now this function has discontinuities, but it's not a countable set of discontinuities. Okay, but you observe that this function is something that oscillates. It's not something that is monotone. Okay, so that's an example. The otherwise, but we shall prove this result now. So without without loss of generality, we assume that f is monotonically increasing. Monotonically increasing means that if x1 is less than x2, then f of x1 is less than f of x2 or less than or equal to f of x2. You see, on the closed bounded interval, that's assumption that we f is monotonically increasing on AB. This is what we are assuming. Okay. Now, why we restrict only to bounded interval? It may appear to be a restriction, but it's not quite. As far as this theorem or the conclusion of this theorem goes, it's not a restriction, as we shall see now. Okay. So, if it's not compact interval that we are working with, okay, the interval is not compact, and that is okay. In fact, compact is the whole compact is the not. It is just closed and bounded. That's what we mean by compactness. So if it is unbounded, then how do you get out this restriction? Because it appears to be a restriction on the interval. So that's not a real restriction in the sense that we can express the interval AB as the union of a countable collection and ascending sequence of open bounded intervals It's a countable collection that we are talking about. Intervals such that the closures of these intervals are contained in AB. Let us give an example. For example, if A equal to 0 and B equal to infinity, that is, we are working on 0 infinity. On 0 infinity, we can write one by n, or you can even write so that if you take the closure of this is inside for any n. Okay. Now, since we are going to consider differentiation, which is a local property, let's say we are not much bothered whether it is on a whole 0 infinity or because we want to discuss this problem. Okay. Now let us look at this now. And once we prove the result for any interval then we can the set of discontinuities on each of these intervals is countable and hence their union is countable. So it is sufficient to prove it on intervals, on bounded intervals of the type AB, because an unbounded interval can always be set as the union of what you call an ascending what you call an ascending sequence of an ascending sequence of open intervals. And on each of these ascending, each element of this collection, you get a countable set of points where you have discontinuity, and the points of discontinuity on the whole interval is the union of these discontinuities. I mean, that's again countable, because you have only a countable collection of such intervals. Okay, right. Now let us explore the discontinuity, the nature of the discontinuity at points on AB. So for each x naught belonging to AB, F has a right limit and a left limit. Has a right limit has a limit from the and from the right. At all points. Why is it so? So this is what you have. It's not at some point. Now you see that the function f is a monotonically increasing function, and the set of points fx for x less than x naught is bounded above, and the set of points fx for x greater than x naught is bounded below. Okay, that is something that is assured by this monotone nature of the functions. And therefore, you see that the supremum exists from the on the set of points associated with the points on the left of x naught, and infimum exists on the set of points so from x naught to b, that is on fx. So let us write it down. Therefore, we can define this. X naught plus, or rather x naught minus, we define as infimum of x over x belonging to this. Okay. And f x naught plus you define as, sorry, this is not the infimum, this is the supremum. Because f is monotonically, you see? And f x naught plus is infimum of x belonging to x naught b. So these two we can define. So you have fx naught plus and fx naught minus. Now since f is increasing, we have f of minus is less than or equal to plus. This is true. Now, from now we can characterize the points where you have discontinuity. So we say that f fails to be continuous at x naught if there is strict inequality in the previous inequality. Okay, this if and only if strictly less than, all this under the assumption that f is monotonically increasing. Okay, so that's clear. Therefore, it says that you have a function. I had drawn this function earlier, something like this. This is x naught b. So you have something like this. So you have this, this. Okay. So this is your f of x naught minus is this, and this is f of plus. So the points where it is plus and minus. Now you see that if it is discontinuous, then there is a jump discontinuity. Otherwise, it is not there. So let us define the open jump interval less than y Now you see this is a set contained in the range space. Okay, this is a part of the range space. In fact, it is this. This is the one that we are talking about. Okay, so I'll just mark this. So this is the open interval that we're talking about. This is Jx naught. So we immediately have, because of again monotonicity comes into the picture, Fa this is the interval Fb, Fa to Fb. Okay, and this is a part of that. Make it close. No. And this we know. Now we also observe that the collection of jump intervals is disjoint. All this is consequence of the monotonically increasing property. Okay. Now let us analyze this more deeply. And you see that each jump that you have at the points of continuity, I mean, it's empty set. Okay, but in other places it is going to be of positive length. So we shall analyze this, the consequence of this. Therefore, we want to essentially conclude that there are only countable set of such jump intervals. Okay, so which essentially means that the set of points of discontinuity is countable. Okay, which implies the set of points of discontinuity is countable. That's what we. So I think it's just one more argument, little argument, will take you to the final conclusion. So what is the consequence of this? Now, for every natural number, n positive, rather, you don't have to write this. For every natural number n, there exists only finitely many jump intervals of length greater than that's our main plank for that. For every natural number n, there exists only finitely many jump intervals of length greater than 1 by n. How do you conclude that? Suppose there are infinitely many. Okay, then what happens? You know that all these jump intervals are disjoint. Therefore, the total length of jump is the sum of the lengths of all this. Okay, and therefore it will have to be infinity. Okay, because it is going to be greater than 1 by n into the number of such intervals. Okay, so that's going to be infinity, which is not true because fb minus fa is finite. Okay, so that's the argument, right? Now this is because if it were infinite, if it is infinite, then we would have the total length of discontinuities with and cannot be contradicts the fact that is finite. Okay, so that's the problem. Therefore, for every natural number n, there exists only finitely many jump intervals of length greater than 1 by n. Okay. So what happens? What is the conclusion of that? For each n, there are only finitely many whose length is greater than 1 by n. Therefore, if you account for all the discontinuities, okay, then you see that it has to be necessarily counted. Thus, the set of discontinuities thus the set of discontinuities of f is the union of finite sets, and hence, therefore, so this is a proof for the conclusion that if the function f is monotone, in the sense it is monotonically increasing or monotonically decreasing, in either case, the number of discontinuities of f is countable, at most countable. So that proves the main result regarding the continuity of monotone functions. Okay. Now to convince ourselves that we have such functions existing, will construct such a function. That's what we are going to do next. So let us construct increasing function with countable sometimes it may be useful in some contexts. So let us do it. So we will have the statement of the theorem. Let C be a countable subset of AB. Then there exists an increasing function on AB, that is on the complement of C, that is the interval slash, that is on the complement of C. So this is very constructive. See, actually demonstrate what that function is. An explicit construction. Now, if C is finite, then it is trivially true, because what you do? It's a set of points, say Q1, Q2, etc., Qn, right? And you can also assume that we have order this set, and Q1 less than Q2 less than etc. less than Qn, and lies between on the interval AB. Now what you do? We will start defining this function. So on the interval A to Q1, we define the function to be, say, 1. On on 1 to the open interval, Q1 to Q2, you define it as, you get a jump, see, something like this. I got A, B, working on this. Now you have, say, Q1 and A equal to Q0. So what you have? So this is equal to. So you can define this function as something like this. Then on this something bigger than that, and so on, and eventually on this define it as something. So you get a sort of increasing function which is constant everywhere except the points Q1, Q2, etc. Qn minus. So that is the construction. So you say if C is finite, it is true. So see this. Okay. See this construction. So that gives it. Now we assume, therefore, let us assume that. Therefore, we assume and it is countable. So we can list out the discontinuities and let C be enumerated as Qn. Okay, so we'll designate this by this one. Now you see, I am not assuming that it is an order relation, because you see the problem is this: you may have the limit point or maybe limit points at different places on AB. So for instance, see, you may get some limit point here, some limit point here, and so on. You will see that there is a crowding around of these QNs around that. Okay, so these are the sort of limit points that you may have. So there will be a crowding around of that. So I am not assuming. So we are not assuming. Monotone sequence. Because there could be limit points somewhere in between. Okay. Then now we define the function. So define, we have to define it at every x f on AB. We are actually constructing a function as f of x equal to summation of n over n such that Qn is less than or equal to x. Of 1 by 2 to the power. So if we take a point x, now look at all the QNs that are on this side. All the QNs which are on this side. Or you will take somewhere here. So you take all the QNs on this side. And corresponding to each QN, you take 1 by 2 to the power n and sum it up. So it gives a value of the function at the point x. Okay? Right? Because Q1 may not be here. For instance, Q1 may not be here. So that term will be missing. Corresponding to 1 by 2 will be missing in that case. If Q1 and Q2 are on this side, then you see that the terms involving 1 by 2 and 1 by 4 will not be coming in this sum. Okay? Whereas this may be an infinite sum, because if you have some point where there is going to be a limit point for this sequence, this sum may be an infinite sum. So this is the definition. This is well defined. See, what we did in the finite case, we could just order them and redesignate. But this is not possible here because of there may be some interior points of AB where the sequence may have their limit points. That's the reason we cannot. So that's why that is taken care of in this definition. So we take the sum over empty set is set as Q. For instance, suppose you take an X here, and there may be no Q's on this side. In that case, you are getting a sum which has no points at all, and that is set as 0. That's the meaning of that. Okay. So note that this is a convergent geometric series. Therefore, this is finite, and that we have. Now, that ensures that that's clear. Now we want to assert that this is an increasing sequence. Okay. So, if A is less than U, less than V, less than V, then we have FV minus FU. This turns out to be, you see, you use the definition, it's very simple. This is the sigma summation over all n such that U is less than Qn, less than or equal to V. 1 by e to the power n, and which you know is greater than or equal to 0. Okay, so that actually sums up the jump from here to here in the value of the function. Okay, thus f is monotonically increasing function. Now what we prove is that if x naught is equal to qk, so if x naught qk for some k, then f has a discontinuity that means at all points in C you have a discontinuity for that is discontinuous. That's the one thing that we are going to do next. But this is quite simple. If qk for some k Then we have f of x dot minus f of x is greater than or equal to 1 by 2 to the power k for every x less than x. Well, this is quite easy to see from the definition. This follows from the definition. Thus, f this is the discontinuity is at least as large as 1 by 2 to the power k. Okay. Now what do we have to prove? We prove that there are no other points of discontinuity. The function f is continuous at all points that's the next statement. So these are the various steps that we have. Okay. So you see that the continuities are essentially at C only. Sorry, discontinuities are only at points in C. The complement of C in AB, the function is continuous. So let's do that. For let n be a natural number. Then there exists an open interval I Okay, so before that, let me set this. So let x naught there exists an open interval I containing x naught for which for then we have mod fx minus f of x naught is less than 1 by 2 to the power. Now this is a consequence of f fp or fv minus fu greater than or equal to 0. Okay, whenever you have the following equal to summation n for every x belonging to okay, that implies f is continuous. So what we have is there is an interval in which qk does not belong to this for this, and therefore we have this is greater than 1 by 2 to the power, right? And therefore see that you get this can be made arbitrarily small by choosing x sufficiently close to x naught. Now this is what gives the continuity of f at the point x naught. So we have proved everything, that we have successfully constructed a monotonically increasing function on the interval AB, which has countably many discontinuities. Yeah, that's what we have. So that completes the proof of that. Okay. So that's a place where possibly we can stop today. And after this, we try to look at the differentiability of monotone functions. So we will consider differentiability of monotone functions in our next lecture. Thank you very much.